Hey there, weird guy. How you doing? I'm just setting things up. I got Jupiter in here now. And we're going to get going here. Yes, it's Blupiter, yeah. A little Blupiter, yes, that's true. I could actually make it different. I could actually make it Greenpiter. Here, if I just go in and change a little bit of the filtering that I'm working with. So we can make it a Greenpiter. There's Greenpiter. Hey, Charles. It's blue because I'm using a filter to reduce noise pollution. See, I can change it and alter the coloration to help us see things more clearly and a little better. I can also monkey with the contrast a little bit. So if we leave it right about here, for instance, I can take the contrast. I can actually do something else. For instance, I could change the sensitivity like this. See, so some of it stands out a little more. Hey there, Ronald. And I can really blow it out so you can actually see the moons out there to the right and off to the left. But if I drop it down to what it should be, this is the default. Okay, actually, this is with everything zeroed. Okay, so if I want to give myself a little more contrast, I can do that. You see, at the same time, drop the gamma, which is what that's called, and you can see a little more detail there. See, so that's a pretty good rendering of Jupiter that way. I haven't even done critical focusing yet, so that's what I'm trying to do. But we'll do that in a second once I get going. So why don't we start? Well, hello there. I'm welcoming you to the SkyTour LiveStream for today, July 12th, 2018. We're going to have some fun tonight. We're going to look at some pretty odd objects if we can find them. And we are going to have a ball with some of the nebulae. It looks like it's going to be a gorgeous night. And we're going to try and take advantage of that if we can. So let's see what happens as we move forward. And I'll see you in a couple minutes. I guess I was just in a little hurry to get going. So here you see Jupiter, or as Weird Guy says, a Blupiter. It does look kind of blue. Hey, Tim. Welcome. So where are you in New Mexico? Albuquerque area? My cousin had land in Rodeo. So it's pretty cool. I like New Mexico. Been to Roswell. Hey, Maddie. Well, you know what, Weird Guy, I want to tell you that the Martian dust storm is actually all-encompassing. It encompasses the entire planet. So, unfortunately, we're not going to be able to see that. We're going to see, actually, we won't see it because, of course, of the fact that the Martian dust storm is just a big orange pall, I should say. So you won't be able to see much of it, unfortunately. Right now we have Jupiter in here, and Jupiter is looking pretty nice. I'm going to actually try and focus it a little more critically here to see if I can get us a little closer. Yeah, that's looking, I think that's pretty good right there. That's pretty good right there, I can tell you that. Right. I did something interesting the other night. You saw my post in Facebook. You saw that I did this. I actually took the telescope and I pointed it toward the locations of many of the geostationary satellites, and you can actually see the geostationaries as they left trails on the image. Now, the reason they left trails is because I was following the stars, and the geostationary satellites don't follow the stars. If they did, then they would rise and set as the stars do, but they actually stay over the same spot on the Earth. So they stay in the same position relative to the Earth the entire time, and that is pretty cool because that makes us see them a little differently. We can see them as trails when we're following the stars. If we set up a camera on a tripod, on the other hand, then we would actually see that we would have star trails, but then we would have little dots on the view, and those dots would be these satellites. And they wouldn't actually be perfect dots. They'd be dots that kind of wiggled a little, and that's because their inclination to the plane of our solar system, or to our Earth's orbit rather, is such that they are a little bit above perhaps what they call the ecliptic, the extension of our equator into space, or a little below. And they're all around the equator. They're not going around the North Pole, north to south, because they couldn't find their way to be over any one spot on the Earth. If they were, they would end up finding themselves being all over the place. They would just travel through the sky like most satellites that we see. But there's a number of really interesting satellites that are up there. And I found the Sirius XM satellites. I found the satellites that are used by the Dish Network. Really interesting, really cool. And you can see actually some nice detail on Jupiter there. Let me just go in and let's play with that a little bit. Maybe there's something we can do here to kind of make Jupiter pop a little more. I'm trying to make it show some detail, a little more detail. If I drop the overall brightness like that, see, now we actually can see some of the cloud banding a little better on Jupiter. That's nice. It's pretty nice. And then I'll set it all to normal when we go to look at deep sky nebulae, because then the settings we're using for the planets are not the settings you should use for a deep sky, because the deep sky settings are going to be particularly different. They're going to show the nebulae, okay, but hide the sky in the background. That is the light pollution. So it looks pretty nice. I'm pretty impressed with this. This looks really nice. And while we got this like this, I'm going to actually go to a wider angle view here in a split second, and then we're going to go to one location. I'm doing this dynamically. I've not tried this before, so we'll see what happens. I'm going to go a little bit southeast of Jupiter to a spot in the sky that looks nondescript. All right, and we're already there. The telescope will beep when it says it's there. And then we're going to see if we can see one of these little satellites I've been trying to tell you about. All right, so first thing is let me just get a view I can work with here. Okay, so here we go. All right. But is it a Hubble image of the horse head you're talking about? All right, now let's see if I can go here. Here's what I'm going to do. I'm going to do a sensitivity of 12, no, I'll say 20,000. Might be a little light out still for this, but we'll try it. And we'll do a exposure of 20 seconds. It's probably still a little too bright up, but we're going to do it anyway. Just a test. I'm critically focused on Jupiter, so now the stars, of course, will be in the same focus as Jupiter. What am I doing? Well, I'm getting a time exposure of the sky in this particular location. And let's see if there's something hiding in there. There may be. So, we're still a little bright. Hang on. Yeah, I think I'm just out of shot. What I'm doing is I'm actually photographing these geostationary satellites, and they would look like trails. And this one's only magnitude 13.6, so we should be able to see this now. So I'm not sure why we're not seeing it. Let's try moving a little more. One second here as I do this. I'm moving the telescope a little bit more. Okay. Well, that was interesting. I had moved it, and it didn't move exactly where I wanted it to. So maybe the photo I took was unfairly not what I expected, because the telescope didn't do what I wanted it to do. So let's do another shot. 20 seconds at 20,000. It's still going to be as purpley, because the purple is just an artifact of the light pollution filter I'm using, plus the fact that the camera sensitivity, with the camera being warm, will induce a sort of a reddish haze. So let's go see what this shows us now. 20 seconds. Well, it did move it over. I don't see it. Well, no matter, because it might be that the data is not correct. So we will find out, won't we? The other night when I was looking at the geostationary satellites, it was like, wow. I saw no less than 4 in one shot at one point. And I think you saw that on the Facebook post that I made. Really something else. I'll do something dynamic now. I'm going to get out of this. Go into 4K video mode. And we'll see if I can do something. Pull up this brightness up here. Okay, that's pretty bright. But you know what? I gotta set my filter settings for this to the default. That's one of the problems that I have here. I didn't do that, so I'm going to do that now. So one moment while I do this. This particular song always sounds like at the end of Saturday Night Live. Thank you all for coming, and that kind of thing. Don't know if you can hear the music actually. Okay. So let's see where we're going here. Okay, we're moving. Trying something here, so bear with me for a sec. Oh yeah, right through the center. See that? That's the satellite I was trying to find. That's a little satellite called RBSP-B. See that? That's cool. So now we can kind of follow it along here as it moves across the sky. Yeah. It also was in the process of dimming out as it crossed the Earth terminated. It's a very slow-moving satellite. Okay, that particular satellite that we just saw, it's 15th magnitude, and it's in Scorpius. It orbits right now, and it orbits the Earth every 9 hours. So it puts it about between 15,000 and it has an elliptical orbit. So 15,600 and 30,760 kilometers up. So that was neat. I was trying to find that, and we found it. Oh, well, Ronald, you have satellite internet? Yep, it sucks. I'm sorry, because I had that at one point, and the downlink speed was very poor. So now we know that if things are buffering for Ronald, that unfortunately it's Ronald and what he's doing, sadly, because he's got that internet, the satellite internet. I did have that at one point, and it's too bad you have that, because what that means is I couldn't put this observatory out there on your postage stamp, Ronald, because if I did, then I wouldn't have the ability to stream, because I wouldn't be able to get an uplink speed high enough to do what I do. Because I'm sending up music, I'm sending up video, and motion sometimes. And that eats up a lot of bandwidth, you know. So what do you say? Okay, now Ronald, you're also saying all of the satellites move the same speed in orbit? That's actually not true, Ronald. Yeah, I'm streaming at 60 FPS. Yeah, and Ronald, about the satellite speed, I just want to correct that for you, because I know that you're interested in knowing what's going on. The higher the orbit is, the slower the satellite can move. So I don't know if you read my post on geostationary satellites that I just put up the other day, but when you look at a satellite like the International Space Station going over, it's moving 17,500 miles at 252 or so miles above the Earth. Well, you can imagine that satellites that are higher than the International Space Station, they don't have to move as fast because the gravity pull from the Earth is less at higher altitude. So they don't have to move as fast in orbit to stay in orbit. So you can imagine there's a point then where a satellite can be moving at exactly the rotation rate of the Earth. Okay? And that distance is around 22 to 25,000 miles out in space from the Earth. Okay? So if the International Space Station was at that location, it too would be over the same spot on the Earth all the time. But it's not. It's only 250 plus miles over the Earth, so it's going to go around the Earth once every 92 or so minutes. And the astronauts will see 15 or 16 sunrises and sunsets every single day. And if that doesn't mess with your mind, I don't know what would. But that's something that would actually be pretty interesting to see. I just want to see one sunrise and sunset from space. Is that so much to ask? You know? I'm going to stop recording the video here for a sec. We did our job. We actually saw the satellite, and I recorded it. So I'm actually going to keep that video. So let's go to another location that might be fun. I'm kind of waiting for it to get a little darker. All right, and let's see. How about here? Oh, I did image these guys the other night. Let me just go here and see if we can image these guys. This is another another set of satellites. They're actually above Jupiter. They're above Jupiter, and they should show. They should show up. Okay. Here we go. Okay, now I'm going to do an exposure. And we're going to do a 20 seconds at 20,000 once again. And let's see what we get. Let me just make sure that we're all fine here. Okay, here we go. And there it is. So we're off and running. Now, if this works, we should see several trails for satellites in the view. Okay, so we'll see. Okay, it didn't work, and the reason is because I forgot to bring down the sensitivity settings. My apologies. 320,000 is just right out. Okay, so let's do it again and see if we can see these. And now I can see that the photo is gonna, or if the images, if they're gonna be there, they're gonna be on the left side of the image. And you should see 2 or 3 of them, if they're there. The blue Danube is one of my favorite pieces. Alright, are we there? I already missed them. I'm looking. I do not see them, so that means I missed them. See, the thing is, we're following the stars, and they are not. Alright, so I'm going to try and catch these. Okay, I'm going to pull out here. Now let's do this again. Let's see what we get. I did this the other night, and it was just totally successful, so I don't doubt that we can do it again. Another thing you'll notice is that these satellites are clustered at various spots in the sky, around the same area. Like, you'll find that they're all around the equator. And I didn't see them here either. What's going on here? I don't know if you can see any dashed lines in there, little tiny lines. Wait a minute. Let's see what I got there. Very faint. On the left side, there's a very faint one. Yeah, very faint one there. Hey, Daryl, how you doing? And I did a little bit of Jupiter, and then now what I'm doing, Daryl, is just checking out the geosynchronous satellites. Oh, there they are. If you look on there, I see them. And I had to get up close to my own screen. I apologize. Okay, here's where they are. Check this out. Okay, let's see here. So we come in and we look over here, and there you see them. See those two? Those two lines? Those two lines are the geosynchronous satellites. Those are actually the telecommunications satellites called the Intelsats, right? The lower one, the upper one rather, is Intelsat 31. And let me see what the lower one is here. And the lower one is Intelsat 30. So that's Intelsat 30 and 31 that you're looking at right there. Isn't that cool? So if you know where they are, you can actually hunt them down. Now, it's not quite dark enough yet. So you're seeing the screen is pretty bright. And I gotta, deal with that. But the thing is, this is the kind of thing I was doing the other night, which I thought was really cool. Because you get to see these satellites, and I kind of like that a lot. So let's see if I can adjust this a little bit. Yeah, you can kind of see them there. Let me just see if I can shift the color a little. Well, that sort of does it. You can actually see the lines there, but again, these the satellites are actually a magnitude 17.5. And for an understanding of what that means, it means that the magnitude of the satellites is 1 million times plus fainter than the star Vega. Okay, over 1 million times fainter. That's what we're looking at here, these two satellites that you see leaving that trail. As it gets a little darker, the sky contrast will be darker, and we will see the satellites show up better. It was pretty cool. Yeah, Daryl, he did. He asked about, Daryl asked if W13, if he asked about seeing the dust storms on Mars. The dust storms are featureless, you know, to most telescopes on Earth. We don't. They're pretty much featureless because they're just high altitude cloud carrying fine dust about the consistency of talcum powder. So that's unfortunate, but that's unfortunately what we have to deal with there. So let's see now if we can. I want to try and find. I want to see if we can find more satellites that are actually very bright. I bet we can. So I literally have like 500 or 600 here I can look up it up. I don't think that we want to do that. We're going to look at some other cool things too, don't worry. I want to try and find something interesting. I want to find a good arrangement here. Oh, this might be a good arrangement. What do we got? 17.2. Viasat and Star 1, and I have Star 1 C2, Star 1 C4, and what's this one? Let me look at. Okay, let's just go there and see it. This should be interesting. And we're moving, as you can tell. Okay. I'm going to set my defaults to like this right here. Subtle hue shift, just to give us the ability to see a little better. Okay, so let me do a picture now. Oh, actually, you know what I just noticed? On this picture that's still showing, you can see the third satellite too. Interesting. You see the two lines in the center, but then above it is a third line. I wasn't looking close. I didn't see it. So all three satellites that I was looking for are there. I didn't think they were. Well, anyway, let's capture these before they drift. Because, as I said, the telescope's following the stars, but it's not following. It's following the stars, but it's not following the satellites. The satellites are doing their own thing. They're over one spot on the Earth, so they're not following the motion as you would expect. They're following the Earth. So here we go. Let me make sure I got my settings right. Yeah, I do. Okay, so this is 20 seconds. And let me just move over a little more. Okay, and here we go. Okay. 20 seconds at 25,600. And we're going to see if we can find the Star 1, C2, and C4 satellites, geostationaries, and the Viasat 2 geostationary satellite, which is, we were trying to see 3. They're going to be around the center of the view, maybe a little to the right. Whoops, I guess we don't have to worry about that. There they are. How about that? Well, there we go. You'll also notice that it passed, the Viasat actually passed a bright star, which is kind of cool. This is fun stuff, guys. This is kind of cool stuff you can do, you can try. Now, it's getting darker. Now, these satellites are the same brightness right now as the other satellites we just tried to take a picture of. But they show much brighter because of the relative change in the contrast of the sky in 5 minutes since we took the other picture. Okay, so there you go. There's 3 geostationaries there. Now, you say, well, again, it's over the same place on the Earth, right? Hey, Keith, how you doing? And it is, okay, but I'm tracking the stars. The geostationary satellites are tracking the Earth. So they're looking at one spot on the Earth. So they're independent motion to the stars. But you can see now I did a 20-second exposure, and in 20 seconds, we could actually measure the length of this. Actually, we could calculate how, in 20 seconds, hi Nancy, we could calculate how much the Earth is rotating just by measuring the length of this. And in the future Sky Tours, we'll do that because I'm working on a system by which I can illustrate stuff for you live on the screen, and that's actually something that works pretty well when it works. But when it doesn't work, all it is frustrating. So, but I did. I'm very pleased that we were able to do this now to show that, because that was a very important one to show. I wanted to show that very clearly, and we did. Okay, so that's more like the proper color. And, if I wanted to drop down the gamma, I could actually make it more of like a really cool spacey shot. But then we would miss details if we were looking at details. Okay, so we're going to keep the detail up. All right. So yeah, there you go. That's Star 1 and 2 and the Viasat-2 satellite geostationaries. And we got thousands of them out there. You can just keep going over, and all you have to do is move west, take a shot, move west, take a shot, move east, take a shot, move east, take a shot. They're along the celestial equator, and that's pretty cool. Now what I'd like to do is to try this. I'm going to try and I went to this spot yesterday and I took a shot of these satellites. These are the Amazonas satellites, and there's several of them all in the same spot. And I'd like to just see if we can get all of them. There's going to be 3 of them, maybe more. And what's funny is I say maybe more because it's kind of crazy the way this thing works. As you can tell, I got some pretty good calculating power to figure out where these things are. And that's blended with the scope so I can find them. And earlier tonight, we actually tracked a satellite moving across the sky. If you're still here, Keith, that's what we did. And I would love to bring you in, Keith. The only thing is, for some reason, Skype is now missing here. Oh, look at that. There they are. That's cool. So let's go back to those one more time. So there's, you can see 2 satellites moving over the same spot of the Earth, and then another one down below. Okay. And so you can see that that the Amazonas 3 is the, which one is which now? Okay, and we're all, again, these are 17.2 magnitude, so these are very faint. Okay, we have the Amazonas 2, Amazonas 3, and Amazonas 5. Those are those satellites. Our Amazonas 5 is the one at the bottom, and Amazonas 2 is the one to the rightmost one of the upper 2, and then this. So the fact that we can see all these things out there shows you just how many there are. We got so many out there. Now, at the moment, this puts us just a short distance from another object that we're going to look at. So here we go, and you'll enjoy this one, I'm sure. Yeah. And there are some of you that probably already suspect where we're going. But because, thanks to Keith, he showed me a couple of things that were interesting I didn't recognize with, the broadcast software I could do. It gave me an opportunity to try something cool. And I'm doing it. So let's try this. Let's zoom in on you. Focus a little, or drop down the... Yeah, by now you know that's Saturn. And you would tend to think that that object just above it is Titan, and you would be right. Titan's actually almost planet size, you know, so that's actually quite a big planet, or quite a big moon. Sorry, I'm doing two things at once here. I apologize. All right, so now let's change the exposure a little so we can see if we can get some detail here on Saturn. Oh yes, indeed. Look at that. That's pretty. Wow, that's pretty. Looking really nice. I'm liking that. I'm going to take a quick exposure of this, if you don't mind. So it's going to be 0.6 seconds at an 80th. And now we can actually zoom in on it and see what we got. No, not bad. Cool. And then the live view is, we're back to the live view now. I like Saturn. I can actually dim that a little more, can't I? Then I'll play with the settings on the camera, on the broadcast software, sorry. All right. I'm bouncing around in here, sorry. That's nice. That's pretty cool. Oh, thanks for that, Daryl. That's pretty cool. So let's jump in here and see if we can modify a little bit and get myself a little more detail. Sometimes the way the eye picks up color, it can show you things that you may not be able to see directly, and that's kind of interesting. Let's do this. What if we do that? Does that help us? Not really. I can see that we're getting a bit of graininess there. I hate graininess. If we can reduce the contrast a little bit, we get to nothing. But okay, that's normal. That's whacking the color up there, but you can see the blue. And this is in black and white. You can see some interesting features on the planet. I think, are we seeing their ring shadow? Maybe, I have to just check. I think we're actually seeing, we might be seeing one of the, actually one of the northern belts on Saturn. Saturn has the same constituents as Jupiter, just it has a rotation period that's just over 9 hours, so it's a little faster than Jupiter, but its equatorial belts are a lot wider than Jupiter's. So for planets that are similar, I mean, the yellow color in Saturn's atmosphere is due to the ammonium hydrosulfide that's in there, and ammonia ice crystals in the upper atmosphere of the cloud decks. But Saturn itself doesn't have any of those deep red hues that we're used to seeing on Jupiter. And that has to do with the relative amount of impurities that are in the atmosphere. And, you know, there's some ammonium ammonia, of course, and there's actually a fairly hefty supply, obviously, of hydrogen and some helium in Saturn's atmosphere. The difference, I think, that people may not understand is that the central core of Saturn is thought to be actually rocky. So it's a rocky core, okay? But that rocky core is like 10 to 20 times the mass of our own planet. So Saturn's massive, okay? And then you've got thousands of miles of atmosphere from that rocky core outward. You know, and the thing that's interesting about Saturn beyond that is it's the only one of the outer planets that has a very visible ring system. Jupiter has a ring system. Uranus and Neptune have a ring system. But the ring system there are made of radiation-bathed organic compounds, and so they're actually almost jet black, and they show up only in backlight usually. Very, very hard to see the rings of those outer planets. Saturn is, on the other hand, very different rings. They're mostly icy particles, and the difference, of course, is that the rings of Jupiter and Uranus and Neptune are made of small powder-sized particles. But Saturn's rings are actually anywhere from particles of that size to blocks as big as small houses and vehicles. So Saturn's got a tremendous variety of sizes for the ring particles. So I'm thinking it's that's something to think about too when you look at this. And I just realized something that I probably did not. Yeah, see, that's an asteroid. Yeah, I kind of got the wrong date there on my thing here. I'm gonna have to just edit that name a little bit and see if I can change the name. And just get that changed, which I can do. All right, and this is now the, pardon me while I do that. Meanwhile, just enjoy Saturn while I go do that little housekeeping. I can't believe I didn't do that. It's like, duh, that was silly. You know, very silly. Okay, I'm back to it now here. Okay, here we are, live streaming. One moment. If you have any questions, you can go ahead and ask. I'll be back with you here in a moment. Okay, here we go. There we are, 7:12. Just changing my title here. I can't believe I didn't do this before. See, I was so excited about streaming that I just went and did this without even thinking. No problem. I think we're okay now. Alrighty. So there. Now I'm back to you here. Okay. I will watch it, Daryl. Sounds pretty cool. Okay, so we saw some geostationary satellites a little while ago. We saw Jupiter, we saw Saturn. Now we're going to test the night, and we're going to see how nice the night is by going a little bit over to the right of Saturn here. And that takes us to another really interesting nebula. And that nebula is called the Lagoon Nebula. So let's just move to the right by just a short distance. In fact, the telescope isn't even going into full gear because it doesn't have to in order to see this. And now I am going to have to set the camera settings a little bit more sensitive so we can see this. All right, and I'm going to go up to 25,600 ISO sensitivity, and I'm going to go to 20 seconds. And there you go. We see, that. Now you say, well, what is that? Is that the nebula? Well, if we go to the live video mode, okay, and we do this video mode, well, now you can see the nebula there. I use this mode to actually center things up too. Okay, so now we have this, the Lagoon Nebula centered in there. I'm very interested to see how it looks tonight because I came out here the other night and took a picture and took my breath away. So let's see if my breath is going to be taken today. Okay, this is a 25 seconds at 25,600, and off we go. Now the Lagoon Nebula is a favorite place of mine. I've really enjoyed this nebula, and it was one of the first nebulae that I viewed as a kid, and I found myself thinking, wow, the lagoon is probably the closest thing, besides the Orion Nebula, it's the closest thing to that, wow, it's a little too bright, but I can change my settings, hold on. Wow, it's going to be another one of those nights. Lagoon is the closest thing to the Orion Nebula for the summer. Let me just, let's bring that back for a sec. All right, and now what I'm going to do is let's change the contrast a little. Let's drop some of this down, and we got to set the hue a little differently. Oh my, look at that. I just say, wow, it's like you can't, the color is going to be off because we're using filters, and I color correct once I take longer exposures and do this later. So I will color correct all this later. But look at that, that's beautiful. That's absolutely beautiful, So, the lagoon is, again, like I said, it's one of my favorite places. It's been one of my favorites for a long, long time. And it's in Sagittarius, and it's a very, it's a stellar nursery, actually. So when we look at it, we understand, that it's 4,300 light years away. It's not close. And to the right, you see an area in here, and I can zoom in here to show you. When you look to the right side, okay, which is right. I'm centering it now. That area, the brightest part of the nebula, right there. It's even overexposed here, but what we're seeing there is there's a hot young star, an O-type star. One of the hottest and most massive stars that we have in our galaxy. And this particular location is where this hot young O-star is located. And this hot young O-star is literally responsible for lighting up that central portion of the nebula and probably a lot more. Now, when I say lighting up, I don't mean reflecting light. I mean, it's causing the hydrogen gas, which glows red, as you can see in here, is taking that hydrogen gas and it's exciting it so much, right, throwing so much energy into it, that the electron around the hydrogen proton that's circulating around the hydrogen proton in that electron cloud is lost from the atom. And that's what we call ionization. So that electron leaves the hydrogen atom, And now the hydrogen atom has a net charge of +1, if you want to think of it that way, because the electron is -1. Together they make a 0 net charge. Well, now it's an ion, a positively charged ion. Now, a positively charged ion will try to attract a negatively charged particle. And there's all kinds of free electrons running around in this nebula that were blasted off the atom by this hot ultraviolet light from this O star. And so these electrons will randomly and spontaneously charge back into the atom through the mutual attraction. But as they do, for them to come in, they release energy. And as they release energy, it's in the form of light. And that light is the characteristic red color of hydrogen that we see in these regions that we call hydrogen 2 regions. And that means singly ionized hydrogen. And you might wonder, well, if it's singly ionized hydrogen, why are we calling it H2? And that 2 is a Roman numeral 2, not a number 2. Okay, why is it an H, II? Why is it an H2, not H1? Well, because H1, Roman numeral 1, is the base state of the atom. So when it has an electron in it and the net charge is 0, that's the base state of that atom. And so that's hydrogen 1. And it's sort of an understood thing. So when it gets ionized once, it goes to 2. When it gets ionized twice, which hydrogen can't do, it goes to 3. What can do it, though, is oxygen. And when oxygen gets ionized twice, doubly ionized oxygen, we call it a forbidden line because it doesn't happen naturally on the Earth. And I'll tell you why in a second. But that, when the electrons that are ionized and thrown out of the atom make their way back in, they drop a few energy states, and as they do, they give off light. That light is characteristically bluish green. So when we looked at the other night, like at the Dumbbell Nebula, we saw, we definitely saw a very bluish green object. I'm going to change the settings here just a little. I'm going to drop us down to 20 seconds. I'm going to go down 2 stops. So I'm going to go 20 seconds at 20,000 ISO and not 25 at 25,600. Why? Let's just see what happens. We might be able to see the dark areas of the nebula a little more clearly if we do this. So when oxygen and hydrogen do this ionization and recombination of their electrons coming back, they do give off light, and that's the beautiful shot I wanted. And when we look here, okay, now this, and weird guy, you got your large monitor going. That's good. So yeah, you see the dark lanes in there. Now, I was going to tell you about that oxygen line being what's called a forbidden line. Here's why. Doubly ionized oxygen can't be made in an atmosphere like our planet. It's got to be made in a gas that doesn't have a lot of density. It's lower density, that is less atoms per cubic centimeter. And when we see that, we figure that this type of situation, this type of location and environment is a place where oxygen can doubly ionize, and we can get that bluish green line, that bluish green color rather. And these atoms are truly emitting light at that point. So that's why when we look at this nebula, okay, we call this an emission nebula. Now it's a hydrogen alpha, or the H2 region, same thing. And the hydrogen alpha emission line is at just about 650, 3 nanometers or so. So it's like 65, 62 or whatever it is. I can't remember what it is, 6523 or something like that. Angstroms. Angstrom is the old unit. We use nanometers now. But it's a characteristic emission when the electron recombines with the hydrogen proton in the nebula. And it's happening everywhere, and it's happening a lot. And when it recombines, it's giving out light in every which way, every direction. And the combined result is what you see here on the screen. All right. Now, you might think, since it's starlight, hot starlight, that is exciting these atoms to do this process of ionization and recombination and glowing, giving off light, Will they always be doing this? And the answer is no, they will not. When that O star in the nebula, okay, that I showed you before, it's inside that bright pinkish spot to the right and just below center. When that O star finally goes supernova, and it will, it's going to create a supernova remnant in this location, but its emission that is creating this nebula glow is in the ultraviolet. It's high energy right now from the star. When that star is gone, the nature of this nebula is going to change drastically. In maybe 1 million years or whatever, this nebula might not be known as the Lagoon or as a nebula at all. This might be a Sagittarius supernova remnant is all that we'd see here. But man, this is beautiful. And supernovae that are close to us could hurt us. This one's 4,300 light years away, so it's not going to hurt us. And again, just to mess with your heads more, those of you that know this, you can just ignore me. But when we're seeing this nebula, we're seeing it as it was 4,300 years ago, because it takes 4,300 years for the light to travel here from there. Think about that. 4,300 years traveling through the empty vastness of space to make it to us. And then we get to see it. Isn't that wild? That is just crazy. But it's how big space is. It's how big the universe is. And there are people that just don't want to believe that, and they don't think it's true. But the fact is, it is true. And I don't know how to say anything other than that, they just have to really pay a little more attention and understand a little bit more astronomy. There's a person right now that's questioning my every statement, not here in this chat, but on my Facebook page. And I kind of think he means well, but he sort of has a predilection toward not believing anything that's being told to him in astronomy and or science. And it's true that science has failed some people very miserably, and it's not their fault, perhaps. Maybe it is, but science has failed some people, and I wish it wasn't the case. But we may come back to this object, by the way. I just want to take us, since we're in the neighborhood, why don't we take a stroll up to another nebula that's right nearby? And it's going to only be just a short distance away. Yeah, look, we're already there. I'll show you when we get there. So let's go take a look at this. Let me move over a little. Okay. Alright, let's do another one. Now we're going to do 20 seconds again at 20,000 sensitivity ISOs. Okay, so ISO. I keep saying the word sensitivity to remind you that the ISO is the sensitivity. Oh, weird guy, I didn't see that dot you're talking about. Okay, what did I miss? Oh, my mistake. I actually I sent this to a different location. I thought I was sending us one place, and when that showed up, I was like, hey, what's going on here? Alright, let me get this down to where we belong here. Sorry. It was a pretty field, nonetheless. Oh, I see why. Yeah, I'm controlling the telescope with an iPad. So many times we won't actually get to see what the iPad is showing us on the screen. It doesn't work out right sometimes. I do not know why, but that's the case. Alright, let me go see what's going on here. Why is that? I'm going to do 20 seconds here. Let's see what I'm doing here. that lagoon is really beautiful. Yeah, there we go. Yeah, that is the Trifid Nebula. I thought I saw a little hint of the Blue Nebula, and I was like, what am I doing there? I'm supposed to be in the middle of it. But I didn't actually put us into the middle of it properly. I actually touched the wrong star that I wanted to go to. Yes, this is, as you can see, this one is really nice. You get some really cool, you can see some really cool dark lanes in the Trifid Nebula there. And by the way, these lanes have changed a little since I was a kid. That lower one is delineated slightly differently than when I was a kid. I remember that being very different. So again, the nebulae do change their morphology, throughout time, and most of them, they don't change in a way that we can notice right away. But over 50 years or so, you can notice changes. We've been looking at the Crab Nebula, which is a supernova remnant in Taurus. Crab Nebula has been viewed for over 100 years or even more, and a record kept of it in photos. And the Crab Nebula now shows changes in that 100-year time. We can actually see some tremendous changes in the nebula. You can see that it's expanding. So the universe that seems to be immutable, that is not ever changing, does in fact change. Let's do another photograph, and for the Trifid Nebula, I'm going to go up to we're going to say 25 seconds at 20,000 here, and we'll let it take that shot. Now, while we're doing that, I'll tell you about the Trifid a little more. Again, one of my favorite nebulae. It's a beautiful nebula. Again, it's a star-forming region, but it's really kind of interesting because it's a double. It's a double region. It's actually got a reflection nebula that's blue near the top, and you have an emission nebula down below, which is that the redder one. Now the colors are, like I said, it's off a little bit because of we've got the colors set to be able to show you the detail in the nebula a little bit differently. But maybe if I just go in here, I can just go play with it here and maybe show you the little difference. Okay, let's do this. Okay, all right, now that's more the realistic color. Okay, and that's the Trifid, and it shows a little differently. It shows a little differently here because we're looking at it in just a simple singular exposure. Okay, but let's talk about the differences. Okay, that upper nebula, which you can just barely see, it's blue. It blends in with the blue filter color, unfortunately, so it's hard to see. Overall, that's called the reflection nebula, the blue part, and the red one down below is the emission nebula. And this nebula overall is 5,200 light years away. Okay, and it's got a hydrogen emission and the H alpha emission down below, and that's from the hot stars down in that center of that nebula that are ionizing the hydrogen in that region, and then when the electrons recombine, they give off that characteristic light we've talked about so many times. But up above, it's a much simpler process. Up above, it's just dust grains and dust in that region around the star, and that star happens to be just a hot star, but not hot enough to ionize any of the gas that might be there. And so all we see are reflections off of the dust. And so the upper part is a reflection nebula. The lower part in the red is the emission nebula. So it's an emission reflection nebula. It's both. And it's a beautiful example of that. All in one view, and I really like that. But isn't this cool? I think this is really cool. Hey Jello, what's up? What's happening, man? Thanks, Dave. How you doing? Is that my Dave Shock Band? That's him, huh? Nice to see you, Dave. You got your internet back? Everything's happy now? I'm glad you're here. Glad y'all here. Yes, sirree. Yeah. I can tell you this. If you, in a dark sky area, you can actually see the Lagoon Nebula with your eye. And some of you can pick out the Trifid Nebula here. Now, an interesting thing about the Trifid, I just want to kind of just sort of like zoom in just a tad, just to show you something interesting. If we zoom in on the Trifid just a little, boy, this is so pretty. Okay, you see those 3 dark lanes in the Trifid Nebula? Those are actually a dark dust lane that is in front of the nebula. The nebula is not actually divided into 3 parts. That's actually a dark molecular cloud that's sitting out in front of the bright nebula behind it. And so you're actually seeing sort of an illusion that makes it look like it's cutting it into 3 parts. It's not. That's just snaking gas and snaking dust that's not ionizing. So you don't actually see any kind of red glow coming from this location in particular. It might also be, far enough from the star, forward of the star toward us, or such that it may not be, it may not be obvious how it's laid out, and so you might think you're supposed to see, they're all the same distance. You might think that, but they're not, and we have to really understand that that's the case. And yeah, I think the Trifid Nebula is really looking good. This is looking pretty tonight. So that's the Trifid Nebula right there. Very, very pleased with that image. It's so nice. And then just north of the Trifid, we're going to go to this, and I'm going to get us back into the live mode here so we can see it come in as we go. This is, now we're going to a little star cluster, which you're not going to be able to see right away. There is a bright member of the star cluster, and that's showing up there on the screen. Right? But what's hidden in there, all right, and I'm going to drop this down to like 13 seconds at 20,000 just to see if that'll show it. This location is, for instance, what happens after stars form in one of these stellar nurseries, like the Lagoon or the Trifid Nebula. And let me just move us a little. You can see it there. That's actually that's Messier 21. All right. Now, let me explain what's going on here. When we look at something like this, when we look at one of these types of clusters, all right, and I'll just do a quick shot again. When we look at these clusters, what we're seeing is the leftover result of star formation that occurred in a stellar nursery like the Lagoon or Trifid Nebula or the Orion Nebula. And that's perfect. And we see the stars after all the motions of the stars and the gas from which they were born have kind of played out with each other enough so that the gas got dispersed and the stars took up residence here and are all gravitationally bound. They're all moving around the galaxy, and perhaps they didn't move at the same speed as the clouds of gas in which they were formed, or maybe they dispersed it with their stellar winds. But you see a lot of star clusters that are isolated like this, and this isolation is the direct result of the fact that these stars, once they were born, their stellar winds actually took care of pushing a lot of this stuff out of the way. Very nice. It's really cool. I really enjoy stars and seeing them in clusters like this. Now as we move forward, as we move farther up, I'm just going to go here and we'll take a picture of this location. We're going to move up now. And we're moving farther north. We're moving up toward another object. But before we get there, I just want to take one deep shot of this location and see what we can get. We might not see too much, but I want to try and do it anyway. So this will be 20. I'm going to take a 25-second shot at 32,000 ISO. And we'll see what we can see. 25 seconds at 32,000. Then I'll tell you where we are. So this location that we're in now is actually a location called the Sagittarius star cloud. And it's a very, very dense region of the sky, a very dense region of the Milky Way. And as you can see when you look at this image, it's definitely very well populated. There's a lot of stuff in here. Now, off to the right there is a little cluster called NGC 6603. And that little cluster that's in the star cloud area is 1,200 light years away from us. The star cloud is significantly further in the background. And if we took a longer exposure of this location, you would actually see that there is stars even in the darker areas that you see there. There's literally, we're looking kind of right now toward the center of our galaxy. So we're looking into the densest part of our galaxy right now. And I love just looking at these locations because you can actually see so much and see so many things in here. And look, there's a beautiful red star there. There's a beautiful double pair down below. And there's a red star in that. And we don't know if that, I'm sure that star is actually not in this cluster here that we're looking at. But we're looking at these things, these star cloud, and it's just a beautiful location. And when you take a picture like this, I would so expect and so enjoy just looking over all the many stars that you can see. And then, Daryl, you're asking a question that's actually very prescient. That there's a small window that's in our, when we're looking toward the galactic center, there's a small window where we can see a little further past all the stars. Because it's like being in the forest, not being able to see out through all the trees. But from above, you can make out the sides of the forest and its shape very well. Well, the same is said for our galaxy. We don't even really quite know what our galaxy looks like. We infer a lot by looking at other galaxies and to figure out what our galaxy looks like. But we don't really know. We think that we thought we were for a long time that we were just a spiral galaxy, like the Andromeda galaxy is a spiral galaxy, like M33 in Triangulum is a spiral galaxy, like M81 is a spiral galaxy in Ursa Major, in Ursa Major area, and but the fact is, our galaxy has turned out to not be a regular spiral galaxy. It's actually a barred spiral. It has a bar of heavy-duty density down through its center, and the arms come off of that. I think that's pretty interesting, So the Sagittarius star cloud is a fascinating location, and as Daryl says, you're right. It does provide a window to the center of our galaxy. And because we're doing this tonight this way, you're not gonna find me doing many photos of this all at once, and then doing any kind of processing on it. Okay, because I would have to be out here for a long time, and I'm not going to subject you to that. So I'm going to just modify the colors here and see if I can pull anything else out of this that we might want to see. We can increase the gamma here a bit, and alter the contrast. I mean, you can see how many stars can make themselves evident from this process. I mean, there are so many stars here that we can't even begin to count how many there are. But it's okay. You know, I'm okay with that. I like that we can't count everything. I'm okay with that. I just think that it's a beautiful location. Again, in black and white, it would look like this. Now, when I was doing research, we often took photos in black and white because color actually added problems to our calculations. Because, you know, colors don't focus all at the same spot. So it's kind of hard for us to have film, for instance, or photographic plates or sensors that would detect color properly. So we often used filters that looked at specifically one type of light from a star. Like, for instance, only the hydrogen light. You know, hey Dave, thanks for coming. Glad to see you. Oh, I see. Now you want to... Oh, there you go. Show them Saturn. Dave, show them Saturn tonight. It's really out there. Jupiter's good to see, and Saturn. Perfect. You'll be a hero. And Mars is risen too. So Mars is over on the eastern end of the sky. And we'll check that out too. So I'm going to show you guys what I mean by this. Yeah. Yeah. No worries, Jello. Thanks for coming by anyway. Yeah, so this is the Sagittarius Milky Way. Let's now go to one other spot that is one of my favorite locations. And we're going to leave the star cloud behind and head to another star-forming region not too far away. Actually, it's just right up the Milky Way. And the telescope is barely moving because it's almost there. So that's kind of cool. All right, and let's go there now. So here we are. Doesn't look like much, but if I were to just do a 4K video moment and we kind of start to increase the sensitivity, then you can see there's something there. And we'll pull that up. That's why I like the 4K. Okay, this is another nebula that's a star-forming region, but it's a nebula with a caveat. This particular nebula, and I'm going to delete this because we don't need it. This particular nebula is one where we thought that star formation was going, and this will be 25 seconds at a more reasonable. It'll be 25 seconds at, I'll do 25,600. It'll be bright. And this is a nebula where we saw that star formation was happening, but it turns out that the star formation has apparently ceased or has been much lessened in this area. That's kind of an interesting feature because it shows us that these regions do have a lifetime and do have a time limit. Even though there's much hydrogen left over, apparently the geometry of the cloud is such that there's not a whole lot of star formation going on at this point, which is kind of interesting, very interesting actually, because it tells us that, wait a minute, I don't think actually, oh, my camera did a reboot, sorry. It did a dumb thing. Okay, here we go, 25 seconds at 25,600. This is a nebula called Messier 17. It's 4,200 light years away, and its proper name is the Omega Nebula. Now, that's kind of interesting. There isn't an Alpha Nebula, but there's an Omega Nebula. I think that's hilarious. All right, and when this one comes in, we'll see it, and it has a lot of rich detail. Wow, oh, look at that. It has a tremendous amount of rich detail in the center. Look at that, guys. Holy cow. Wow, that is just so stunning. This is a 25-second exposure, by the way. I think that alone tells us a whole bunch of stuff, a whole bunch of interesting data. And I'm trying to get the real color, as best I can. And right now I'm zooming in to check the quality of the stars. I see that they're slightly elongated, so it's a little bit. There was a little bit of motion, and I thought I detected some. So I'm gonna try now to do it again without bumping the pier this time. and our image should be a little bit more stable. Wasn't that pretty though? I mean, it's like I said, that's 4,200 light years away actually, and it's a beautiful former star formation location. And I will have to say that it's probably again one of my favorites. You know, and if you notice, it has a central core, which is actually pretty bright. And I'm looking again. Stars seem a little better actually, a little bit better. Yeah, the central, they're much better. But you can see how there's like a slight color shift. That's because we're saturating the sensor, believe it or not, with this brightness of this nebula. Very, very cool, and you know, not easy to do with a faint nebula, that's for sure. But look at that. That is just so pretty. That is so pretty. The Omega Nebula. Oh, it's just gorgeous. You know, I love that. And you know, we're not even done, okay? Because now, let's go up to another little location with this telescope, and we don't have to move much. We're only moving at a very slow rate up to this next location, and this is a location of NGC 6605, and this is going to be a location where we have again, we'll do this not 25 seconds. Let's drop this down to, let's say, 10 seconds, a little finder image. Make sure it's there. I could have done it with the 4K video, but I figured why not? We'll do 10. We'll do this. We're looking at NGC 6605, which is a open cluster, and that's an open cluster in Serpens. And you'll notice that this cluster is interesting because of one thing. It's nearly dispersed. Okay, you can see how there's some bright stars around the outside edges, but they're dispersing. Okay, this is a location where they once formed, probably nowhere near this location, but as they migrated around the galaxy, they drifted away from their origin cloud. All right, and it's a fairly big cluster, and we're seeing kind of like a chunk of it, and most of it's off to the left side a little bit. But it's sort of like a little minor foray as we head to something else that is literally just above it, which I think you will like. So we're going to go there now, and it's literally right up the street, right up the Galactic Street. Yes, sirree. I will do a finder shot of it. Actually, I'll do a 4K video shot of it. See what we got. Make sure it's there. Yeah, here it is. That's another nebula, but it's really, really pretty. Yeah. We looked at this last time, guys, and I think you remember. I think you know where we are. I think you know where we are. So, let's go take a look and make sure that what we have is what we expect to see. I'm going to now delete this because we don't need it. And let's just take an image of this location that's hiding in the dark. In an area of a country where there's any light pollution at all, you might barely you might barely just see the Lagoon Nebula, okay? But you'd never see this. So this will be 20 seconds at 32,000 ISO. So you get an idea what 20 seconds will buy you, but 32,000 sensitivity. So, and don't forget, most cameras in the past, they basically they did, 100, 200, 400, 800. Oh my gosh, that's so beautiful. Let me just move this up a little more, a little more. I'm gonna do this again. All right. In fact, I'm gonna go to 25 seconds because I just want to try and tease out a little more detail. And I got the settings in the dynamic view here such that it's maximized for looking at nebulae right now. So I think that we're going to see this. I mean, you saw the Trifid look beautiful. We're going to see this looking pretty. So here we go. And wow. Oh, man. So this region here is one we've seen before. That's the Eagle Nebula. Okay. And those are the pillars of creation that were taken by the Hubble Space Telescope. All right, and that was this region right here in the center that you see. The pillar that has a little red dot on it, that would be the leftmost pillar that you see. And then to the right of it, just to the right of that star, almost in the dead center, is the next pillar. And then to the right of that is another one. But as you can see, this was just, it's a stunning night. This is absolutely beautiful. And so when we look at this, okay, you look at all these nebulae in here and you say, wow, this is something else. And if I actually come in here and play with the processing a little bit more, I could be dangerous with this processing, I gotta tell you. So let me come in here and let's try that, huh? So let's just knock this down a little bit, knock this up a little bit, okay. And about the brightness, let's drop the brightness a little bit, maybe leave it right about there. How's that looking? What do we got? Is that looking good? Flag. Yeah, look at that. Wow, that's pretty. I would also want to shift the hue a little bit. Yeah, see, that doesn't work, and this doesn't work. This is more like the Hubble. This is more like the Hubble palette that they use. Looking at the nebulae, the one we just had there, and then we slide through a few of these different variations, and then when we get to about here, right about there, that's the best one right now for looking at the nebulae, because that's giving us the most detail. But then, like I said, we can take, we can take the gamma, which is now at negative 0.16, and we can bring it up, and around the outsides of that nebula, you can see more detail shows up. But at the ISO rating that we're using, it gets pretty messy. Okay, so we don't want to use that too much. But it's looking pretty nice. I'm glad you like it, Nancy. I just find myself staring at these things. I just cannot get enough, frankly. That's right, Daryl. It's a swan, too, the Omega Nebula. Yeah, we were just looking at the Omega. It's also known as the Swan Nebula. Yeah. Indeed. So, yeah, these nebulae, this is a Milky Way Nebula tour. And while we're here, actually, let's just try and move up. Let's move up to here, another location. You'll recognize this, which is kind of interesting. All right, we're moving up now, and it's right near where we are. And I want to show you something here that we're going to look at. Okay, just gotta... One minute. I'm getting there. Hang on, guys. 1 second. Okay. Now let's do this and see what we get. Okay. Alright, I'm taking a photo again of something that we've already seen. But because it stays over the same place on the Earth, it's moved, but the stars have moved behind it. Okay, because it's staying over the Earth. It's tracking the Earth, it's not tracking the stars. And there they are. Remember these? This is the Star 1 C4 satellite. And on the bottom right, let me just bring it back for a sec. This is the geosynchronous satellite. And you can see the Star 1 C2. And then off to the left, the Star 1 C2 is the upper one. And then you have the Viasat-2 off to the left. And you'll notice that these are really interesting little tracks. And again, these are because of the fact that we're using tracking of the stars to keep imagery. Sorry, I'm doing 5 things at once. I apologize. We're tracking the stars, so we're not satellites. If we're tracking the satellites, then they would be dots, and the stars would trail. Okay, but honestly, this is just beautiful. This is just too nice. Too nice, man. I just love it. I love these, being able to see these. Very cool. Alright, so now let's take a gander at a few other things, which, as we're pushing up now, as you can imagine, we're at the celestial equator now. We were below the celestial equator this whole time. But let's go back down below the celestial equator, to this next object, which is going to be a little bit of a distance away. And so the telescope's going to move us down there now. There we go. There we go. It's very low. It's not up that high right now. But we are going to be able to see it anyway. Because you had asked. You had asked about this, and I want to show you what we're looking at. Okay. This is Mars, as you may have guessed. You may have guessed that. And I want to do a motion. I'm going to move this over a little bit. Okay, and move it up a little bit. Although not much. Not much. Let's try that. Alright, I'm going to do a long exposure. We're not going to see dust storms or anything at this point. I just want to do a long exposure, see if we can find one thing in particular. To make this exposure be 10 seconds at 20,000 ISO. And here we go. Mars is an interesting planet. When we're actually, on the same side of the orbit as Mars, okay? The thing about Mars is that we actually can have time travel to Mars. The time it takes a signal to travel to Mars can be as small as 4 minutes. But when it's on the other side of the sun, on the opposite side of the sun as we are, it can take up to 22 minutes for a signal to get there. And that's life in the orbital lane, Now, why did I take this picture? Well, I overexposed Mars for one particular reason. I wanted you to see that little dot right up to the side there, which you can see when I kind of zoom. Okay, see that little dot right there? That little dot? That is one of Mars' moons. It's called Deimos. Okay. Now I'd show you Phobos, except it's behind the planet right now, so you can't really see it. which is too bad. But that's Deimos. That's probably a captured asteroid around Mars. Really neat. But let's now do a proper photo. Let's do a proper photo. Sorry about the lens flare. That was actually a flare caused by the observatory wall. Alright, so let's drop this down. And let's see. Well, let's drop down the ISO to a really small number. Then there we go. So I want that. Now, how is this going to look when we zoom in? Okay. Now, this is how we're seeing Mars right now. Now, the reason we're actually seeing a little bit of a, you can kind of see some detail on the surface. I'm wondering if that's what that location is. I'm seeing a little bit of a, I'm seeing a breakdown in the color here. I'm seeing it. It shouldn't. I don't think we should be seeing that like that. I don't know why I'm seeing that. Sorry about the noise. I'm wondering if we're seeing an artifact, or if we've got something. There's something behind it, maybe. Don't know. Hey, I'm all for investigating. We've got to figure this out. All right, let's go here and let's see if we can get this into rail color here. About right. That's a little purple magenta. I don't want that. Maybe this. That's a little better. Yeah, see now, that was a little bit of an aberration caused by too high a saturation, that is color content. I should have turned that down lower, which I did, and now it looks a little better. I see detail on the surface. Don't you think? I can see some detail on the surface. It looks to me like we're not seeing the dust storm. In fact, that location is actually, that's actually, I'm looking at that. That's like Terra, actually, on Mars, pretty clearly. And then to its right, right of center, we have again a much larger area. It's Terra Cimmeria. That's Cimmeria, by the way, and that's those little dark areas. So clearly, we're seeing this. We're seeing some stuff. So I'm guessing that at least at this side of Mars, the dust storm isn't really a problem. You know, isn't really a problem. But I am going to do something here. I'm going to do one other thing while we're here. I'm going to actually take a. First of all, I'm going to make sure that we're centered, and I got to make it centered a little more. Okay. All right. And now, with it being kind of like it's centered, I'm going to move us up in here and do this. Okay, that's what I wanted. Yeah, you clearly can see some features, so it looks like it's got some features on there. But what I'm going to do, and I'm going to do this here with you right now, is I'm just going to do a quick 30-second of Mars. Now, why? Well, because each frame is being taken at a 60th of a second, and if I do 30 seconds, all right, that's going to be a lot of frames, okay, and it's going to be 1,800 frames, and the purpose of doing this is that I will have a whole bunch of frames of Mars. And those frames can then be taken. Okay, there's 35 seconds. Those frames can be taken and they can be treated as individual photographs. And then we can take those individual photographs, so to speak, and we can process them to show us Mars in a much more clear fashion. It's image stacking, but with using the video imagery. And you can sort the video images in best or least to best quality, and then use only the best ones. All right. And if I come into the color balance here again, I want to just do that because I'd like to see if I can bring up a little more detail. I could be wrong, but I'm thinking that perhaps I'm seeing a polar cap, but it doesn't appear that it doesn't. It might be a polar cap. That what you're seeing, Daryl? Huh. Yeah, I'm trying to find out. I'm not sure if south would be up, and so I'm thinking that would be the south polar cap. But I'm not seeing on the finding chart. I don't see the polar cap. And by the way, for those of you having buffering issues, hi Starseed, nice to see you. Haven't seen you for a while. For those of you having buffering issues, I'm in the green here, so I'm guessing it's probably or could be your stream health. Your internet health at your side. You might want to check that, because I've been looking at my stream health here, and I've got full network connection. No one's having any. No one's working on the computer in the house, so we're out here just doing our thing. Let me try a couple little things here. If I change the contrast, does that do anything? Oh, look at that. Do you see any features on the surface like I think I do? I'm not seeing things here. I'm just trying to see what we see. Alright, let me drop the saturation a little bit more. Yeah, it's interesting. Looks pretty nice. Looks pretty cool. So that's Mars. And earlier we saw Deimos, and I think that's neat. So I think that we want to take a little bit of a foray to something else that might be interesting to look at, and it might take us outside of the place we're in now with our Milky Way. Let me check here. We can stare at Mars for a while. Wouldn't it be amazing if like something hit Mars just now? A big asteroid. Wow, that'd be fun. Alright. Maybe not. Okay, so I'm checking out something here. All right. One second here. Okay, let's go here. Okay, we're going to go to another spot right now. Yeehaw! Away we go. Alright, we're going higher in the sky. And we're going to go up and away. Okay. Yeah, we're looking pretty high up in the sky right now, which is good. We're up in Cygnus, which is nearly overhead. We're actually only just a short hop, skip, and a jump from the Gamma Cygni Nebula. And we're actually going to be looking at a nebula that's here. I know when you hear Cygnus, you think, oh, maybe we're going to be going to the supernova remnant, the Veil supernova remnant. Not this time. We might check it out. But right now, first of all, let's go up to speed of 32,000, and let's do just 6. No, actually, I'll do this. I'm gonna do this again. I'm going to do a 4K acquisition to see if I can find what I'm looking for. I'm looking now. Here we go. Let's see what we got. Yeah, I didn't think I'd see it in this. Might be a little faint to show here, but I'm going to try it. See if we can find it at 32,000 is with that 32,000, and let's see if we can see it with 15 seconds. And I didn't tell you what it is yet. That's correct. All right, good. I'm glad you. Yeah, weird guy. I guess I'm glad you got it stable. Nancy, I'm worried about you though. How come yours isn't? Wow, look at that. That's it. It's there. So this is the Crescent Nebula, and you can see it there. I'm going to change the settings now. Do the color filters. Try and look at this and see it a little differently. The Crescent Nebula is a beautiful little nebula. Okay, you can see it there. We process this a little bit. Yeah, that's nice. If I bring up the saturation, it's probably going to do that, yeah. In black and white, you can actually, it almost stands out a little more. This is why we used to do black and white a lot, see? Because black and white, it was a simple thing. It was white or it was a shade of gray. And we didn't have color to contend with, and we didn't use color. And that made it a lot easier, actually, for us. I'm going to bring this up a little. I'm going to bring it up just a little bit. So a little more. Okay. Okay. Yeah, Tri-X. Remember Tri-X black and white, Daryl? Tri-X was one of those films that was film that we actually use. Acetate, real film, silver halide crystals, Crazy, man. Crazy. All right, I'm setting the defaults now for the view. And I'm taking I'm going to take a 25-second exposure at 32,000 ASA. Might be a little bright, but I want to see the Crescent Nebula in a little more detail. Now the question is, what is the Crescent Nebula? Well, it's a visually interesting location because it looks like an arc, but it's actually kind of a elongated circle. It's sort of a ellipse. Okay, and it's an object. We got it right there. It's an object that's actually 5,400 light years away, and it's a nebula. Now, the thing is, this thing is a little different from other nebulae. It is an emission nebula. It's giving off light, the same way that the others do. Okay, but it's actually something by it's formed by a very fast stellar wind coming from one of the stars. One of the stars in its there we go. That's a little better. One of the stars that's in its central area. And when we look at this object here, okay, the arc that you see just above there, you can see that one end, the left end up there, is a little more red. Then it goes near the center, it goes through a bright star in that location. And then to the right, it opens up into more of a whitish looking thing. It's actually pink. And it looks like a letter C, you know, and then it continues down and then hooks back in by that other star that's below center, the bright one. This object is generated by this very bright star in the middle. And that star that's generating it is, see if I can move it into the view here well for you. Yes, I can. Hold on one second. Here we go. Okay. The star that's generating this nebula is not that. The star that's generating this nebula is this guy right here in the middle. And I'm just going to move in a little bit here to show you. Okay. Okay, so there, that star right there in the center. All right. And that star is called a Wolf-Rayet star. So it's Wolf, W-O-L-F, Rayet, R-A-Y-E-T. And these Wolf-Rayet stars are very powerful. They have huge stellar winds. They're massive stellar winds. A lot of radiation pumping out. So, you know, it's like I said, it's around 4,700 light years away. Actually, 5,400 by some standards, and you know, 4,700 to 5,400. They don't really know for sure. And the star in the middle, that's designated as a Wolf-Rayet star, WR136. So if you look up WR136, Wolf-Rayet star, you'll get this nebula. And the stellar wind is heading outward from this star, and it's colliding with material out in space, and you know, it's about 25 light years across, and there's a shock wave when it hits this stuff going out, and that shock wave causes the illumination of the edge, as you see here, but then it reflects back inward, and so you get two shock waves. One's moving out, and then one bounces off the stuff as it's going out and heads back in. So we're getting all kinds of heating going on in here, and there's a lot of X-rays being emitted through here. So it's really a dangerous place. Now, one thing they think is that you know, WR136, this star here that we're looking at, is probably going to go supernova in the next million years or so. Because again, very, very powerful, hot star, massive, and just it's going to have a very, very powerful blazing end, I can tell you that. So, but this is the this particular nebula. Again, this is the Crescent Nebula, known as NGC 6888. Okay, and it's really a really interesting nebula when you look at it, because it's got a lot of detail in it. You know, and I'm trying to get the best mix, and this is about it. This is pretty much the best. This is the best part, the best way we can view it right here. You know, but that's not bad. So that's the Crescent Nebula, and I'm very pleased with that nebula, that way it came out. What a beautiful night, guys! Really beautiful night. Really beautiful night. Now, I promised I would go to that supernova remnant. It's right down the road. So we're going to it now. Okay, that star you're looking at right there is 52 Cygni. That's, you know, on the west side, you know, from the directions west, east of the, you know, here on the planet. On the west side, that's actually that's the western edge of the nebula. All right, and we're going to do 25 seconds at 32,000 sensitivity and see what we get. Yes, indeed. Let's see how it looks. That's really pretty. Let's go look at that again. Wow, look at that. Okay, so that is the western veil. Really, really nice. Wow. I do not understand why it's lagging, Daryl. Yeah, it's really pretty. Let's up the contrast on this a little bit, maybe. Increase the gamma, pulls out some of the hidden detail. Increase the contrast a little. Yeah, see, you can easily get to a point where you don't see any detail, but then you can get to a spot like here, okay, where detail shows more, but the color isn't right. That's why we use what's called false color a lot. We'll actually show our objects in a false color because it shows them much better. We know it's not the right colors, but it does show them better, and that's kind of what we're looking at right here. It's sort of a false color. But if you look up north of 52 Cygni, you can see the convolutions and shape of this little tendril of the supernova are just outrageous, incredible, you know. Now I'm going to try, I haven't actually ever tried this section before. I'm going to try to go to a different section that I've never gone to before and see if we can actually see anything here. Yeah, it does, Daryl. It looks like a rope tornado. That's right. You know? Okay, so now I'm gonna move up here. I haven't tried taking a picture of this location in the Veil ever, so I don't know if this will come out. But I want to see. There's sort of like a bunch of very interesting little rope sections here, and we're gonna do 25 seconds at 32,000 ISO here, and we'll see what we get. So here we're off and running. And this is a region now that the Veil is an interesting supernova remnant. You know, it's about 2,600 light years away, and it's the remnant of a star that once was, and we only know by some of the material. Wow, you can see it. How about that? I never did this before. We only know by some of the material that we see what it might have had in it. Look at this. Holy cow. I can see that. I can see that right in the center. Look at that. Wow. Oh man, this is really pretty. Absolutely pretty. We can't get over that. Wow. Let me see if I can show it better. Maybe the contrast? No, contrast kills it. Oh, that's looking pretty good there. Look at that. And then you can see right there, that actually kind of shows that these little tendrils here. Very, very faint. But see, for me, I look at this as a success, because I would actually take this and go through and look at it differently. I would go through and I'd start to process it, you know. So we can try this location here. Now there's another location within the same nebula. There's so much going on here. It's amazing how much is going on here. But let's try this one. This is another area just north of it. And we'll do again 25 seconds at 32,000 ISO. There's a fairly well-defined dark area in here that might show up. I'd like to see it. I'd like to see it. I agree with you, Nancy. Now, tendrils, yeah, I meant tendrils, you know. Oh, wow. Look at that. You can kind of see it. It's again, it's low surface brightness stuff, you know. Very low surface brightness stuff. kind of in the center there. It's hard to see, but it's an area of the veil that's not too prominent, not too visible, I guess. But boy, that looks nice. And now what we're going to do is we're going to go to the eastern veil, the one that we're familiar with, along with the western veil that we saw earlier. The opposite sides of the eastern veil is that beautiful multicolor arc that we've seen before. And I'm going to actually try to actually look at a little bit of a different location of it. Why not, you know? Let's see what's down here. Okay, hold on. Just swatting a mosquito that was around me. So I got one of those little tennis rackets that's, you know, a zapper. And I must have been like, I felt like a little kid running through my house with this thing, swinging it around at the flies that were around my house. And all of a sudden you hear, psh, psh. It's like, wow. Yes, it's a feeling of power, you know. All right. We are on the eastern veil now, or eastern, and I want to actually, this is that little arc that we've seen before, but I put us in a slightly different spot. I want to see what we're going to see. 25 seconds at 32,000 ISO. Oh yeah, look at that. Wow. See, I was trying to get the upper area. And we can see the upper area pretty clearly up there. That looks nice. Really nice. So let's move down now. There's another area that's down below. I want to check it out too. I'm telling you, man, this is crazy, huh? Really is pretty. Okay, so this area here is fairly bright. That's really pretty though. Look at that. And now, if we follow that arc down to the lower left, that's where I'm going now. And we'll see what we can see down there. Again, supernova remnant is a remnant of a star that blew up, and when it blew up, it exploded with such a force that, you know, the universe hasn't seen forces like this except for other supernovas like this one. And this one was relatively close to us. Wow, look at that. This one was relatively close to us. And at the distance of this one, the danger to us was not there. There was no danger to us, even because it was 2,600 light years away, but that's not dangerous to us. But all that wispy stuff you see there, that's areas along the front where the stuff is expanding, where it's hit other material in the interstellar medium and compressed it, ionized it, and caused it to glow. These are emission nebulae now, but they're supernova remnants as well. See, you can have more than one type of thing, and that's what we're seeing here. And when you look at the Crab Nebula is a little tiny patch in the sky, but the Veil Nebula is massive. It's a giant complex, and the size of the complex is just something else. It's like it's literally 6 times the diameter of the full moon in size in the sky. That's how big the Veil is. That's how big it is. It has all this branching nebulous stuff. You can see it right there on the screen. And look at this branches, and this processing that we're doing dynamically is really helping out, by the way, because we can see things that we might not have otherwise seen. So when I come in here like this, for instance, you know, you can just pop right in and say, hey, look at this branching going on here. This stuff's branching out in a variety of ways, and we can see it right there very, very clearly. So it looks really nice. I'm having It's a really good night here, by the way, guys. Really, really good night. So let's now, since we're in the neighborhood, I do want to go to one other place here, and it's just me. I have to go. Just one little place. All right, let me just sorry, I got these skeeters. Okay, I'm just checking this out. Let me see. Okay, and we're gonna go now. And we're still in Cygnus. Yeah. You know, you can't defeat a good double star. Yeah, and this is a really, really good double star. This is Albireo. It's Beta Cygni, the second brightest star in Cygnus. And it's actually a pair of stars that are very different colors from each other. One is a B-type star, and one is a K-type star. So it's it's like an odd combo, you know. Let me move this back to where it belongs. There we go. Okay. So let me also come in here and set my defaults for the colors. And then I can set the hue appropriately. Okay, that's more like it. So you can see that the star on the left is blue, and as it should be. And that blue star is a B-type star. Remember our OBAFGKM spectral class, and that's a B-type star there. Okay, it's actually a B8, so it's just before a B9, and it could be an A star next. So, and then that K star, that orangey star to the right, that's a K8 star. Sorry, K3 type star. So it's a fairly early type K star. All right, so it's just beyond. It's actually just beyond the G that we are, OBAFGK. All right, we're a G2 star, and this is a K3. And now, I really like these stars. They're beautiful. The separation is amazing. They take approximately, I think was it 75,000 years for them to go around each other? You know, I think that's what they said at one point. Just crazy. But it is a pair of stars that are 430 light years away. Okay, 430 light years away. And the separation at that distance, if you recall, we did a sky tour where we actually talked about measuring the distance between them in arc seconds or arc minutes. And these stars are separated by 34.7 arc seconds. And we talked about a calculation we could do to determine how far apart in real space they were, real measurement. And knowing they're 430 light years away, separated by 34.7 arc seconds, we can calculate that means that they are 4,620 astronomical units apart. Now, keep in mind that the planet Neptune, is 30 astronomical units away from our sun. Okay, 30. And these stars are separated by 4,600 astronomical units. So that's like a crazy amount of distance between these stars. Yet they're gravitationally bound to each other. And you can imagine that since our whole solar system would fit very well inside this star, in between these two stars, you have to wonder whether any solar system could exist there. And the answer is probably no. Because the B8 star is really hot, and the K3 is older. Now you may say, well, what does that mean? Well, the K3 is a more orangey star, alright? And so together, between the two of them, they're probably going to be pack quite a punch, ultraviolet-wise. The B8 especially. The K3 will have flares. So this is probably a relatively sterile environment, if not gorgeous. So, you know, that beauty is belied by the lethality of this location to us, which I think is, you know, unfortunate but true, man. So I think that we'll just have to deal with the Earth for now. Let's see now. Oh, what are we going to do now? Oh, I know one that you'd like to see. This is cool. I'm going to take you here because this is another one. Remember that Wolf-Rayet star we talked about with the Crescent Nebula? Well, we're going to go to the one that's not a Wolf-Rayet star, but it's actually one that actually has a very powerful stellar wind that's taking this nebula, or making this nebula, and I think you're gonna like this one. I think you'll like this one. Oh, let's just do a. Yeah, I think the nebula's around that star we're looking at right there, in the middle. So let's go see, shall we? 25 seconds at 32,000 ISO. Now, this location, this is called the Bubble Nebula. And the bubble is 1,400 light years away, and it's a very hot star whose stellar wind is blowing out gas, and the gas is hitting other gas out there in the interstellar medium, and it's in that collision, it's actually made a bubble. And you can see the bubble right there in the middle of the view. Okay, so let me get the color correction here. Let's drag this over a little bit, like that maybe, and bring this down a little. Oh, look at that. So yeah, this is the bubble. You can actually see that arc of the Bubble Nebula right there. That's a really, really beautiful location. And maybe we can zoom in on that a bit. Let's go see if we can zoom in on that a little bit. There we are. Now we pop in. Yeah, so that star is expelling a huge amount of radiation, and that radiation ends up going over and creates this little bubble. Very, very interesting location, man. Really, really cool. And I'm now trying to find something else that might be in this region. Let's go to this one right nearby. And I'm not sure how this will come out because I've never viewed this one before. Not sure. Let's find out, shall we? Alright, let's do the same kind of exposure and 25 seconds at 32,000. This isn't a nebula, though. This is a faint cluster. And I'm wondering if we'll be able to see it. I think we will. This should be measure 52. We're checking this out. The measure 52 is a 4,600 light-year distant cluster of stars. Oh yeah, perfect. And they migrated out of their stellar nursery, or blew all the gas away. And that's how stellar nurseries stop being stellar nurseries, is because they actually have stellar winds blow all this gas away. You know, very cool. Now the cluster distance really isn't that well known, but it's approximately 4,600 light years. So that's pretty cool. Pretty cool indeed. Let's see what else we have. We're just doing a whirlwind tour tonight, aren't we? Yes, we are. Now we can't get down too low to the horizon, which is kind of where we are already. So you don't want to do that. Oh, I know. We're going to go here. That's right nearby. We're going to check out this one. Alright, this is another nebula that's kind of nearby. Let's see if it's there. Yeah, it's there. Alright, now we're going to do the same thing. 25 seconds at 32,000 ISO. And let's see what we see. This is the Iris Nebula. And it's an open cluster associated with a nebula. And then the nebula is a reflection nebula. Remember we talked about when there's dust in an area of space and the bright starlight reflects off it, we call that a reflection nebula. And that's what we're seeing right there. Okay, I'm just going to bring us up a little more. Okay. And let's see if we can... let's see if an ISO of 40,000 does anything for us. It usually doesn't. There's a maximum amount that you can use on this camera. The ISO goes up to 409,000, but the maximum that you would use is around 51,000 at the most. Beyond that, it puts too much noise into the image. You know. So we see this, and let's so that's the Iris. Now let's go and find out if we can process it in a way that looks like we have a little color showing up. Okay, we got that. Let's bring up the gamma a little bit. Oh, my telescope just broke. It's Friday the 13th. Thank you, weird guy. Look at that. This is pretty. If we... a little contrast. Maybe like that. That's pretty. That's very nice. And if we can drop the saturation a little. This is a really... the Hubble Space Telescope took some really nice pictures of this location. It's amazing how much you can see when you're up in space. Let me tell you. Amazing. So the Iris Nebula looks pretty. I know we didn't go look at the Wild Duck cluster. I know that you mentioned that, yeah. And I thought that we didn't go look at that, but we could. We could do that. And I'd like to actually possibly do that because I want to look at the Eagle Nebula one more time before we call it for tonight. Actually, before we do that though, I want to do this guy right here. This is We're going to do the Dumbbell Nebula here for just a minute. I want to measure the quality of it and see how it looks. We're looking at it. No way. Huh. Well, no wonder I was having issues. I was wondering why my telescope was not performing perfectly well, and you know what it was? It was a cloud. There's actually some clouds up there, those little stinkers. Well, that stinks. Alright. And that explains what I was seeing here. The Iris Nebula usually looks a lot better. And I was wondering why it didn't, and I was thinking maybe I had a problem with the telescope, and it wasn't. It's the clouds. We have clouds. Alright, so let's do this. Let's see if we can get any kind of a photo whatsoever of the Dumbbell Nebula. And we'll go there now and check it out. The Dumbbell Nebula is in Vulpecula, and it's literally the remnant of a dying star, actually a dead star. It's 1,400 light years away. It's about a light year across, and it's what's called a planetary nebula. And these planetary nebulae are just the sloughed off remains. Look at that! Wow, they're the sloughed off remains of stars like the sun. As they puff up, as they get older, they puff up, and they end up losing their outer layers. And they do that because of the fact that they are done fusing hydrogen into helium, and they end up having they swell, and when they do that, their outer layers can actually literally become free of the star and just float away. And usually it's at supersonic speeds, maybe slightly less. So when we look at this and we see this object here, we're noticing that, you know, it has a certain amount of color, and I'm going to try and get this color to be a little more correct. It's right about there. We can tune the saturation down a little bit. Okay, and that's a little better right there. Drop the gamma a little, and you'll see the shape better. Okay, that's the Dumbbell Nebula. Now that outer loop you see, that it looks like an hourglass, but then the sides of the hourglass are filled in with other shell materials, and that's what you're seeing there. And that's beautiful. That's really beautiful. The exposure is actually a little too long. What I'm going to do is I'm going to come back here, and I'm going to go, instead of that ISO, I'm going to drop it down to 20,000 for 20 seconds. Let's do 2020 and see what we get. Alright, so the 20-second exposure at 20,000 ISO of the Dumbbell Nebula, 1,400 light years away. Remains of a dying star, now populated in the center by a white dwarf. And as we see this white dwarf, oh, guess what that is? Cloud. That should have been a gorgeous photo, and instead it's a picture of a cloud. Look at that. What a difference, huh? What a difference a cloud makes. She goes from this, okay, to this in, like, 10 seconds. Man. Yeah, that's just, and the clouds are only where I want to be. They're not anywhere else. Figures. Yeah, it figures, It's the only cloud, too. It's the only cloud up in the sky, but it's covering all the places I want to go. Why is it doing this? Who does it think it is? Nah, I bet you we'll have a little shot at it now. Okay, we'll try this again. 20 seconds, 20,000 ISO. Okay, the same photo as we just took with a slight cloud over it. We didn't see anything, but now let's see what we get. Let's see if it's a little different. No. Yeah. Oh, well, yeah, there's a cloud. Alright, let me just try something else just in case I'm messed up here. Let's go. In case I drag the settings for the filters down too far. Oh, I did. My fault. Sorry, guys. Sorry, Charlie. Yeah, I actually had dragged the settings down, so my fault entirely. Okay. But anyway, you can see now the tiny star in the middle, that central star, and we're at a high ISO right now. So that means that we're not actually at the high ISO rate. We're not actually getting the best grain-free view of this. But you can see when we go in the middle here, in this kind of a pseudo Hubble hue, you can see there in the middle there's a central star, and that's a white dwarf. And these white dwarfs are actually they're actually composed of carbon and oxygen atoms on their surface. They're very, very tightly packed, and the material on the surface of a white dwarf is called degenerate, so that it's all compressed together. All right, and this compression is so powerful that the atoms actually press back in the opposite direction that they're being compressed. And the original mass of the star was such that it couldn't compress any further, because the atoms, once they got compressed to the density of this white dwarf in the middle, the atoms wouldn't allow themselves to be compressed any further because of what's called degeneracy pressure, electron degeneracy pressure. And so it pushes out with a force to keep the white dwarf from collapsing further. And it collapses to a point that's commensurate with its mass. For stars that are heavier, it can go right past white dwarf stage, and you end up having a point reached where there's neutron degeneracy pressure, where the neutrons are pressing back at the amount needed to keep the star stable at that size. Let me see here. Yeah, and this is a white dwarf, neutron degeneracy pressure. When we see neutron stars, sometimes neutron stars are the result of supernovae. Sometimes they're preceded by, and this is rare, but they're preceded by a further collapse to black hole status. And that does happen from time to time, and we actually have seen that recently, actually. At least the possibility of that, happening. But this is the Dumbbell Nebula we just looked at, and it has a white dwarf in the center. It's not that. It's not going to be that much of a compression for this. But I want to take us to another object here before we go to the next thing, which may or may not happen, depending on the clouds. All right, let's head down. Let's head down to the southern horizon. See what we can. Not southern horizon, but let's head in this direction. Oh, figures. There's a cloud right where I want to be. Man. This was supposed to be a beautiful night, and what happened? What happened to my night? It's gone. But it's okay. I'm not worried. Let's do a 4K video clip for a second. I want to see where we are. Oh, yeah. That's where we want to be. I thought we would look at this little guy to end the evening. This is the, and I know that you were asking about it in the chat as well. This is the wild duck cluster we're looking at right here. Let me see here. When the wild duck here comes up, I'll tell you more about it. Because, again, it's an open cluster. It's so dense, though. Oh, duh. Yeah, sorry. I did a... Whenever I do the video, the 4K video, I have to set the ISO way up high. And I did it, you know, and I did not take the time to put it back down before I did that photo. So I'm doing it again. And I reduced the ISO actually to 20,000. So it's now 2020. Nope, I'm sorry, I'm wrong. 20 at 16,000. For this particular cluster, 16,000 is all you need. Yeah, look at that, huh? This is a little jewel box in the sky, isn't it? It's a little jewel box in the sky. And this cluster, the wild duck, is and don't ask me why they call it a wild duck. Maybe because it looks like birdshot, you know, buckshot. I don't know. Okay, but it was discovered by Gottfried Kirch in 1681, and was first resolved into stars by William Durham around 1733. And then Charles Messier included it in his catalog in 1764. So it's been known about for quite a while, you know. And the wild duck cluster's name, okay, if you want to know where the name really came from, it comes from Admiral Smith, who noted that its fan-shaped appearance somehow resembles a flight of wild ducks. And I guess maybe the fan-shaped appearance was something that you would see with a lesser telescope, but I don't know. I don't see it. I don't see the fan. Maybe you guys do, but I certainly don't see it. Oh, Nancy, that's just funny. What a cluster duck! Aha! That's funny. That's funny. That's cute. This cluster is 6,100 light years away. Again, the stellar winds from this cluster successfully pushed away a great deal of the gas that was there before. I'm going to up the saturation so you can actually see. You can see the colors. You can see how some of the colors are bluer than others. And if I can just mess with the hue a little bit. Yeah, it's kind of... It's right on the border. Just messing with the hue colors here. Just trying to get it a little better. But see, you can mess with the gamma. See, you can make it look really interesting here. And these are the defaults right here. This is what it wants to default to. Actually, that's not so bad for the cluster. How about that? Neat. So the wild duck is a fascinating location. I love just exploring the Milky Way. You and I, and you guys and I have just ventured through a lot of the Milky Way tonight, which is really kind of fun. And I just want to continue, but it's getting a little chilly in here. And of course we have clouds. Yep. All right, let's see what else we got. As if it's hard to find anything. This is just the most amazing location, you know. Let's go to one more. Just one more. Okay, and this is another cluster. This is a cluster that's may or may not be exciting. But let's find out, shall we? Let's do this exposure. Okay, it's going to be 20 seconds at 16,000 ISO. And as we do it now, I'll tell you the cluster name. It's the cluster IC 4756. So letter I, letter C. That stands for index catalog, by the way. 4756. And there it is. Now, it's a little tiny. It's just sort of a loose grouping of stars, but used to be tighter. Used to be a lot tighter when it was first made. And then the stars, through gravitational interactions with each other, kind of moved apart a little bit, you know. And I think that's typical of these clusters, you know. Now, right near it, if we just want to go over a little more, then we have this one, which you can actually see on the screen now. And we'll see it when I take the picture here again. Right, this is again 20 seconds at 16,000. And this is the cluster, and it's NGC 6633. And it's a 4th magnitude cluster, open cluster. There it is, appearing in the constellation of Ophiuchus, and it's about 1,200 light years away. And then, you know, you get the idea that what we're looking at in these clusters is we're looking at places where there used to be a Lagoon Nebula, basically. There used to be a Lagoon Nebula type thing, and honestly, there's just no two ways about it. You know, when you look at these things, you gotta realize that you're looking at the evolution of a system. The evolution of a system here. So, and I like this little cluster. It's kind of a neat cluster. I like it. I like the other clusters we looked at too. And let's see. Now, I know that some of you are asking for like Uranus and Neptune. I know that Uranus is down below the ground right now, actually. I'd have to point the telescope at the ground to see it. And then have, of course, the X-ray vision on. And let's see. Where's Neptune? Well, why don't we go there? We can go see Neptune, because Neptune is actually available to us. But don't forget, wherever we go to view it, it's going to be on the celestial equator or close to it. It's kind of low. I don't know if we're going to... Let's see if we can see it here. Through the clouds. Hey, there it is. Hello, Neptune. Yeah. Well, there it is. That's our Neptunian friend out there. And the clouds kind of suck, but we can still see it. Okay, and the color of Neptune is just what you would think. It's a blue color. That's Neptune. Now let's take a exposure though. Let's go ahead and take an exposure. This will be let's say 10 seconds at 16,000. It's actually very low to the horizon. So we're probably going to lose the color in this exposure, but that's okay. Yeah, we did a little bit, but it's not bad. So there's Neptune. And right next to it, you can see that little white dot. Guess what that little white dot is? If you guess that that's Nereid, then you would be right. Actually, you wouldn't be right. That would be Triton, which is Neptune's moon Triton just below it. Okay, and Nereid is actually out further. I don't even know if we've got Nereid. Let's find out. Nereid will be out here. Oh yeah. But that's I'm not sure if that's Nereid. That doesn't look like Nereid. Looks too bright to be Nereid. Oh, Nereid might be right above that star, actually. Nereid might be right above that star. Interesting. But yeah, but that's, you know, since Weird Guy asked for it, I figured we'd show it, you know. Amanda's not available tonight, so we're doing this without her. So I'm actually watching the chat along the way myself. So, yeah, but you got Triton and Neptune right there in one shot. Really, really pretty. Very, very pretty, actually. And Nereid's out there. Boy, that's just an amazing solar system we have, let me tell you. Let me tell you, boy, it's beautiful. So, well, I gotta tell you this though. I'm gonna be yes, I know, Daryl, it's true. I'm gonna be heading in here, and I'm gonna be closing down the stream for the night. But I wanted to thank you guys for coming out. I really enjoyed your company, and I'm very happy that you guys came along for the ride to see all the many things we saw tonight. And I hope that you will come back and join us again. And I look forward to seeing you guys the next clear night. Because every time it's clear, you can bet your butt I'm here. And that rhymes. Anyway, hope you guys have a good night. And we will close out the night with Neptune here. So I say good night to you, and remember to keep looking up. Good night, all.